Okay, the last part of chapter 18 and the last example of types of problems that happen in chapter 18 are these big conceptual tables. And this is just a way of trying to organize everything you know about entropy, enthalpy, spontaneity, reactions, kinetics, pulling it all together. So to go through one of these and how I problem solve one of these, I'm going to do an example. Okay, so bromine is one of the few elements that exist as a liquid at room temperature. Its melting point is 265.8 Kelvin, and its boiling point is 332 Kelvin. Like all liquids, if you place bromine in a container, it will evaporate until it reaches its vapor pressure, creating a rust-colored cloud above the solution. Predict the thermodynamic parameters for the evaporation of bromine at 298 Kelvin. So the first thing that I like to do in these problems is actually write out the reaction that is happening. So we have bromine liquid going to form bromine gas. And the first question that we want to answer is this process spontaneous? And so what we need to think about is, does this thing happen? Does it occur? And the answer is yes, it does occur. If we put this in a container, it will evaporate. So we use the context clues in the problem. And so now, since we know it is spontaneous, that tells us that the delta S of the universe is greater than 0. It is the delta S of the universe is positive. Okay, and so this means also that we know the sign of delta G, because we know that this reaction is spontaneous at the temperature that we're talking about, at 298, and so that means that the sign of delta G is going to be negative. If reactions are spontaneous at that temperature, then the Gibbs free energy is negative. Okay, so we went from spontaneity and we answered everything that we knew based upon answering that question. So now I'm going to move to, is the product more or less ordered than the reactant? And so this is looking that our products are gases, and so those gases are less ordered than liquids. And so from this, it can tell us something about delta S of the system. And so this is looking at the system, and so we know that our delta S of our system is going to be our S standard of our products minus our S standard of our reactants. And so since our products have more entropy than our reactants, we know that our delta S of our system has to be positive. Now, we also know something about this one, because we know that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And we have already determined that delta S of the universe is positive, delta S of the system is positive. Oh, we can't do this one yet. We don't know delta S of the surroundings yet. We'll get there. Okay, so now, what is the next one on our quest is what is the sign of the entropy of the surroundings? And we can't quite get there yet because we know that delta S of the surroundings is equal to negative delta H of the system divided by temperature. And so we need to get delta H of the system before we can get up there. Okay, so entropy of the system, going from a liquid to a gas, we have to add energy, and that means that this is endothermic. And that means that delta H is a positive value. And so now that we answer this one, we can come up here to delta S of the surroundings. Since delta H is positive, delta S of the surroundings is going to be negative. And so now we can combine these into this magnitude question. And so we know that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And so the universe is positive, the system is positive, the surroundings is negative. And so this means that delta S of the system has to be greater than the magnitude of delta S of the surroundings, or the delta S of the universe will not be positive. And so our answer here is greater than. Okay, now also with knowing the entropy of the system, it will also tell us about the enthalpy of the surroundings. I'm sorry, did I say entropy? I meant enthalpy. Because we know that delta H of the system is equal to negative delta H of the surroundings. And so since our system is positive, our surroundings has to be negative. So now that we know about delta S of the system and delta H of the system, we can think about this process being entropy or enthalpy driven. We have delta G equals delta H minus T delta S. Delta H is positive. Delta S is positive. And that means that the T delta S is what is allowing this reaction to be spontaneous. And so this is an entropy driven system. I have this question in here twice. I think this was supposed to be, what is the sign of delta S universe? It is positive. Okay, now at what temperature is the process non-spontaneous? This is asking high T or low T, all T, or no T. It's not actually asking for a value of temperature. And so in this case, the reaction is going to be not spontaneous when the value of T delta S becomes small, because delta G equals delta H minus T delta S. And so if this T delta S is a small value, then delta G will be positive, and this isn't going to happen. And so this is going to be true at low temps, which makes sense. If we lower the temperature, stuff doesn't evaporate as much. And then the last question is a question thinking back to the beginning of the semester. Bromine, oh, I missed the subscript 2 up here. Bromine is a nonpolar molecule, and so that means that the only intermolecular forces that it has are London dispersion forces. Okay, I hope this made a little bit of sense. These tables take a little bit of practice. You do have one in your lab, but you can also find some others in the homework that the homework and the exams that I have posted on World Class.